Everybody, thanks for coming today. Just real quick background on myself. I was a practicing mechanical engineer in Canada for 10 years before I came to Singapore, and now I'm a ESD consultant. What I specialize in specifically is energy optimization, decarbonization, and the application of emerging technologies, specifically with the goal of energy reduction. So today, I have 10 minutes to give you a crash course on dynamic air change systems. So to kind of lay down the groundwork, we're going to answer the first question, what is an air change rate? Second one is, why do labs consume so much energy? Sarah kind of touched a little bit on that, but I'll kind of dive a little bit deeper into that question. And how does a dynamic air change system work, and how much energy is actually saved? So, question number one, what is an air change rate? So this is a diagram of a very typical lab. We have some fume hoods, open lab area. We have supply venturi valves. Some people call them VAV boxes. We also have exhaust venturi valves. When we talk about an air change rate, I'm going to walk through how we actually calculate that. So the first thing we do is we take the volume of the lab itself. That's the volume. And an air change rate is a volume of air to completely displace in a room within 1 hour. So it's a very simple metric, actually. So I'll walk through an example on how we actually come up with a number. So let's say we have a 10 meter by 10 meter room, and it's 3 meters tall. To calculate the volume of the room, we go 10 meters times 10 meters times 3 meters. That gives us 300 cubic meters. Agreed? So, so when we say one air change rate, that means it's 300 cubic meters per hour. And when we say two air change rates, it's 300 times 2, so that's 600 cubic meters per hour. Agreed? Yeah. Yes, okay, great. So in Singapore, to answer the question why labs consume so much energy, there's a standard called the Code of Practice for Fire Safety for Laboratories Using Chemicals. Very long title. SS 641 is what it's more commonly known as. It mandates that for sprinklered buildings, for sprinklered laboratories specifically, you have to have 8 air changes during occupied hours and 4 air changes during unoccupied hours. And that is a system that's on 24/7. So that's occupied hours, 8 air changes, and then when everybody goes home to sleep, it's still running, but at 4 air changes per hour. It never turns off. It's not like an office building. And that's because of the sort of prevailing opinions about fire safety, making sure that we're not exposing the building occupants to sort of toxic chemicals. And this is all governed by SCDF. So very, very strict requirements, and pretty much every single lab in Singapore is designed to these standards. So 8 air changes, when we go back to the original example, 1 air change rate was 300 cubic meters per hour. So 8 air changes is 2,400 cubic meters per hour during occupied hours and 1,200 cubic meters per hour during unoccupied hours. So when we design the system, what mechanical engineers typically do is they size their venturi valves to provide that 8 air change rate. And then on the exhaust side, it's a little bit more just to make sure that the lab itself is negatively pressurized. So you don't get sort of the toxic fumes getting into adjacent spaces. Now, the reason why, or this is the key reason why the labs consume so much energy, is because all that air is 100% outside air. So in Singapore, that means the design temperature is 32 degrees Celsius outside, and then we have to bring that temperature down to between 12 to 13 degrees to properly dehumidify. Now, on top of that, to get the right relative humidity, so what's comfortable in Singapore is between 60 to 65% RH, you then have to heat that air up back to a level that's comfortable for the building occupants. Which sounds crazy, right? We cool the air and then we have to heat it back up in Singapore just to be able to control the humidity. Doesn't make sense. But that's how the field of psychometrics, this is how you have to design the system in order to get comfortable thermal comfort conditions within the lab itself. So when we translate 8 air changes to a lab, that works out to be about 350 watts per meter squared at peak. That's just for cooling. Now when we compare that to a typical office, that's 90 watts per square meters. So that's 3.5 times, more than 3.5 times of energy consumption just to condition the lab. And this is basically the bottom of why labs consume so much energy in Singapore. Actually, not just in Singapore, but in general. So the answer to reduce the energy consumption is the answer is actually really simple. It's just, let's reduce the amount of air that we're delivering into the labs. I'm really simplifying the issue here, and I'm just going like really the key points, but the solution would be to implement a dynamic air change system. So what Sarah said is that rather than just having the system on all the time, you have a system that responds to what's actually happening in the lab itself. So the way a dynamic air change system works is it senses the indoor air quality within the lab itself. So it's constantly monitoring what are the different contaminants, particulates that's in the air, and then it reduces the air or increases the air as in response to the changes in concentration. So that way we're only delivering the amount of air that's really required. So for lab spaces where a lot of experiments are happening, there could be contaminants that are coming into the air. If the concentration spikes, then the system would increase the amount of ventilation that it's delivering into the space. Once the concentration of those contaminants has reduced, then we can go back down to a lower air change rate level. So the system is not operating 100% all the time. This is the example to illustrate that. So the idea is, instead of the 8 air changes that we had initially, the baseline, we set it to 4 air changes, and then we reduce also the amount of exhaust to 1,260 cubic meters per second. Again, just a little bit more of exhaust to keep the space negatively pressurized. So if we reduce the air change rate from 8 to 4, that means our watts per meter squared goes from 350 down to 175. So that's a 50% reduction in your cooling load just by implementing this control strategy. And going back to SS 641, a question we get a lot is, are we allowed to do this? And the fact of the matter is yes, we are allowed to do this within the framework in Singapore. What it says here is that you can do a further reduction in your regular air change rate down to 4, provided that you go through this Annex B risk assessment. And that's basically telling us that you have to continuously monitor your indoor air quality for contaminants. And the system has to be able to control the air change rate. So if there's a spike, then it goes up to 8, and then you can go back down to 4 once you've cleared the contaminants. And then you also have to lay out the lab in such a way that your fume hoods are in dedicated rooms, your open labs is a separate room, your biosafety cabinets are in a separate room. That's a generally already standard practice, so it's not a big hurdle to overcome. So this is going back to Sarah's presentation. So what's NUS doing towards greening our lab? So we were the consultants that were involved in the energy modeling study that was done earlier. And what we did is we basically worked with a manufacturer that provides this demand control ventilation system. And we modeled what the energy reduction would be, and we also modeled what the actual thermal comfort impact would be. So we went into the lab, we cataloged all the equipment that was in there. We looked at the mechanical drawings, and then we basically replicated the building or the lab space within an energy model, and then played around with the numbers to see what would happen when you change the air change rate from 8 down to 5. Is the space still going to be comfortable? Are we actually going to see energy reductions? And the answer was yes. What we actually found was that the space was completely overcooled, and that aligned with the observations that we made in the lab itself. People were wearing coats, and then on top of that, they had their lab coats on. And then in some cases, the room was so cold that we just suspected that perhaps some of the reheat coils and things like that weren't working. But the conclusion of the study was that it's feasible, we can keep the space comfortable, and there is energy savings associated to it. So why is this not widespread in Singapore? I already talked about some of the regulatory requirements. Mechanical engineers do tend to be a bit more conservative. And I speak for myself. I was a mechanical engineer and I was very conservative. But I wanted to just highlight this study that was done in North America. ASHRAE Journal published a study where it was basically monitored indoor air quality across 8 facilities. Within those 8 facilities, they monitored 300 labs and a total of 1.5 million hours of lab operation time. They implemented the demand control ventilation system, and then they monitored what is the change in the concentration of various contaminants. When you look at this graph, so this bottom axis is the volatile organic compound concentration, and this is the percentage of time over the threshold. So this is, the system is working, so it's sensing the changes in concentration, and if there is a spike, then we're increasing the ventilation rate. If we've met the set point, then it's reducing the ventilation rate. And the results were quite interesting. It basically said that 99% of the time during this study, that's 99% of 1.5 million hours of operational time, they were able to run the system at 2 air changes per hour. So that means that there was no impact to health and safety, and there was no impact to any sort of research either. And so 99% of the time, they were able to operate at that lower air change rate. And that's sort of the end of my presentation. Hopefully that sort of illuminated a little bit of how these things work on a mechanical level. I know that was very, very quick, but if you wanted to learn more about it, please feel free to reach out to me on LinkedIn. I could talk for hours about it, and I was forced to condense it to 10 minutes today. Thank you.